Hi there. In the following video I'm going to solve for you the Chinese Postman problem, or the route inspection problem as it's otherwise known as. Before I do that, I want to show you a little puzzle you may have seen before, just to get us into the right frame of mind for this. You've probably seen this when you were younger. Can you trace the following three different graphs, we're going to call them now, so that you meet every node and you go over every edge just once and only once without taking your pen off the page. So you may want to pause the video. I'll pause for 10 seconds. You pause, see if you can do that with the following three graphs. Off you go. Okay, let's just have a look through these. It actually turns out that with this particular graph here is very straightforward. I'll start any way you want. I'll start here. I'll go like as follows. Remember, sorry, where I started. I started here. Let's just retrace. So I went. Let's say I went up, across, and back. And I ended up where I started. I can start anywhere. I'll have another go without any thinking at all. This is very straightforward. I'll just start. Why don't I start here? And let's see where I get to. And I ended up back where I started. It seems with that one, wherever I start, I end up back where I started, and it was very straightforward indeed to trace my steps around that whole graph. It turns out in this particular one, I can start only here or here, and if I start here, I'll end up here, and similarly if I start here, I'll end up over here. Anywhere else is no good for starting off. So let me just show you an example of it. If I start here, I can go like this. Okay, so I end up at the, and I go over here, and I end up to the other one. And if I start on this side here, without much thought, I can go round the houses here, and I end up on the other one I started at. Do notice that in the first graph, I started and ended in the same place, whereas in these ones, I started here, ended here, or if I started here, I ended here. The final one, actually, no matter what you do, you're not able to solve this one. So if I go across, down, up, I always end at a point where if I go up here, I'll have to retrace my steps in order to cover this one off, and it will always work something like that. No matter where I start, it's no good. If I start here, I'll always have to somehow retrace steps to get to the other one that I've left out. Okay, just going to talk a little bit about these particular graphs. You'll remember the term order of a node means the following. The order of a node is how many arcs are coming out from the node. Here there are 2 arcs. Here there are 1, 2, 3, 4. Here there are 1, 2, 3, 4. Here there are 1, 2, 3, 4. Again, you'll find there are 4 arcs coming out here, 4 arcs coming out here, and 2 arcs coming out here. Let me do it with this particular graph here. It's 2, 4, 4, 4, 3, and 3. And this one here is 3, 3, 3, 3, and finally 4. Now, what was special about this particular graph, I could start anywhere and get back to where I started without taking my pen off the page, because the order of each node was actually even. And this had a special name for it. This was called an Eulerian graph. Now, this particular graph here was a fairly decent graph. I could trace it out without taking my pen off the page. However, I had to start here or here. I had to start at one of the odd nodes, and I ended at the other odd node. So I could do this tracing out here, but I didn't end up where I started. But this was called a semi-Eulerian graph. And lastly, this one has more than 2 odd nodes. In fact, it's got 4, so it's a non-Eulerian graph. It's not an Eulerian or semi-Eulerian graph. This meant because I had more than 2 odd nodes, I could not trace it out here. Okay, this is going to be useful to us when we're dealing with the later work with the Chinese root inspection problem. Move on to that now, and then I'll come back to why the orders mattered in these particular cases. Okay, here's the Chinese postman problem, or the root inspection problem. A real life problem is over here. The postman starts from his post office here at the corner, and he has to walk along every single street and return to the post office when he's giving out his mail, and in the least possible distance he can. So he's got to start at the post office, walk along every single arc or every street, return to the post office, and do it in the smallest possible distance. If I translate that into a network problem, let me just show you what the graph would look like, or the network would look like. His post office was here, this point here. Now, he can travel over here to this point here, where he'll have an option of where to go after that. So he'll travel over here to this point here. And there's a route between there, there's a path between these two. Then he's got another corner there, or node there, where he can travel to. But notice he can travel directly, or he's got this other arc route. So he's got a multi-arc here. So then he ends up going to this final point here, where this is his final point here, where he can go to. But he's only got one way to do that. Now let's just think where the key points are here. Should there be a node up here for him to go there and then across to that node? Well, no, that's not a node here. This path between here and here, there's no choice for him at this corner here. There's no choice for him to go anyway. Once he's going in this direction, he stays in that direction. So actually, there's no node there. The next node is where there's a decision to be made about what direction to go in. It's here. So the next node is here, and we're just going to represent this distance here by a straight line here. At this here, he can either go down to this node, or he can actually go diagonally across to that node. Lastly, he could even go over to this final node here, which I'm just going to show with a line there. So this is the network problem of that real life solution. The postman wanted to walk along every road, return to where he started in the least possible distance. This translates to, in a network situation, traversing every arc in this network and returning to his start node here in the least possible way. So that's the Chinese postman problem. Now, can I do that here? Well, just remember what I did in the previous slide. I worked out the orders of each of the nodes. You'll notice that the order here of that is 2, 4, 4, 4, and 2, because there are 2 arcs from here, 4 arcs from here, 4 from here, 4 from here, and 2 from here. And I said that if all the arcs have even order, it's called Eulerian, and we can start and finish wherever we want and end up there easily. So if I start here, I'll easily trace out a route for us, let's say something like this, and I've got back to where I started. Now think about this postman. He has to walk along every road because he has to walk every road to deliver his parcels, and in this particular case here, I've walked along every road once and returned to where I started. So I couldn't do better than that. So in this case here, I found the best solution because it's an Eulerian graph. And it meant walking along each road precisely once, and that meant I returned to where I started. Okay, here's another problem. Very similar problem, but let me just show you the slight difference here. Again, a postman starting off here wants to walk around every single street and return to where he started in the least possible distance. For the graph or network for this, starting with the post office. Here's the post office here. So I'm going to draw in a node here for the post office. Now, if he can walk along here to the other place where he's going to have a choice about where to walk. So I'm going to draw another node here for this particular one, and he could walk along that path there. He could also walk up to this place here where he has another choice. So I'm going to give him a path to walk up here. And lastly, he could have walked across to here to this other one here. He could walk across to here. So I'll give him that choice there. Let's just fill in what he could do from here. Say if he was to walk up this path, he could go that way or that way, and this way, this way would bring him back down to this node here. So I'm going to just directly join them up like that. He could either go from this point, he could go across to where there's another choice or node here. So he could go across here, there's another choice. And then he could go across here to the final choice. So there's another choice here he could go across to. Now, let's just keep filling in. At this point here, he could go up to another choice above him. There's another choice here. He could go up there. From here, he can either go left or he can go right back down to this node. So he can go down to that node, or he can go across right to where there's another choice of where to go. So there'll be another node there. At that point, he can go down, or he can walk down to another choice of node, which is over here. So I'm just going to draw that as a direct line there. He can walk to that point. From here, he can go along there or across, and at that point, he can go this way, that way, or up. And that then is the graph or network of that particular problem here. Now, I just want you to have a think about this before we do anything. The first thing I'm going to do is, like I did last time, write down the order of each node. Here, there's 2 arcs, so it's order 2. Here, there's 1, 2, 3 arcs, so order 3. 1, 2, 3 arcs, 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 order 3. 1, 2 arcs, order 2, 1, 2, 3, 4 arcs, order 4. Now, what type of graph is this? It's not Eulerian because it's got 1, 2, 3, 4, 5, 6 odd nodes. It's not semi-Eulerian because it's got 6 odd nodes and not 2. So it's a non-Eulerian graph. Now, for the postman who's going to start here, in order for him to be able to walk around all the different roads and return to where he started, it has to be an Eulerian graph. Well, why is that? Let's just think about why it has to be Eulerian, for example. If this here is odd and he starts off here, it means he leaves via one path. He must come back later via another path and leave again. So that means he can't finish where he started if it's odd. So that means this one can't be odd here. Now, why do all the others as well have to be even? Well, let's pick anyone in particular. Let's say he has to come into this at some point. So he has to start off by coming into all the other nodes. So say he comes in, then he leaves. Then he leaves it, but then to complete that street there, he must therefore come back in to that particular node. Now, once he's in that node, he can't leave via any path that he hasn't traced out already because he's already used all those paths. So he must have to double up on himself. That's why each of these will have to be even at some point, so that when he comes in, eventually, for it to be even, he will have to leave it via a different path. Now, let's just rub this bit off here. So hopefully that gives you a little bit of insight as to why the order of the starting one has to be even, and all subsequent ones have to be even as well. Because if they weren't even, it would mean that you end up getting stuck in a particular arc with no way out of it. So the aim of this game, therefore, is to make all the odd nodes even. Now, how do we do that? Well, the first thing you might say is, why don't you create an arc between an odd one? Let's say between the odd and the even here. If I created an extra arc, it would make that one now even, so that solved one of the problems. However, what it's actually gone and done is it's made an even one now odd, which is just put the problem from over here to over here, which is no good to us. So I think it's pretty clear what we're going to have to do there. In order to make them all even, what we're going to have to do is link up the odd nodes. So we're going to have to ask ourselves, well, we're going to have to, for example, here's a way. If I linked up that 3 and that 3, then that would be of order 4, that would be of order 4. If I linked up, let's say, that 3 and that 3, that would be of order 4, that would be of order 4. And finally, I could link up that 3 and that 3, and they would all be of order 4. Now I can trace that particular graph, and I'll show you. If I want to start here, let's go like this, any way around we want to go down, across. It's very easy for me now to trace all the roads, including the new ones I've created, and get back to where I started. So the Chinese Postman problem is all about traversing every arc in a network so that you get back to where you started. In order to be able to do that, we need to make all the odd nodes even by creating a multiple arc between the pairs of odd nodes. Okay, so let's get on and actually have a go at a proper question. I'll show you the algorithm first of all. The algorithm, as I said, gets us a way of traversing every arc in the network and returning to our starting node in the least possible weight. Our general aim is to make every odd node even, so that we're making a non-Eulerian or semi-Eulerian graph an Eulerian one. And we're going to try and do this in the minimum possible distance. I'd advise you to pause there and write down this algorithm so you've got it. But I think the best way to do this algorithm is actually via an example and looking back at the algorithm as we go along. Okay, here's an example. Now remember, the postman is starting off at point A here. He wants to walk each particular road, get back to where he started in the least possible distance. Now, if this graph was Eulerian, if every node had order 2, then he would only have to walk along each one once and he would end up back to where he started without going over anything twice. So, to start with, and step 1 works out for us what the total current weight of the graph is. Let's look at algorithm and step 1, add up the weights of the arc to work out the total weight of the network. We add up all of these, so we add up 45, 42, 35, 38, 40, 28, 62, 70, and 80. And you get 440. Now remember what this means, step 1, that is, if this was an Eulerian graph, that would be the minimum possible distance in order to traverse each arc and return to where you started. Okay, what does step 2 say? Step 2 says work out the orders of each node, identifying the odd ones. Let's see if this is Eulerian or not. Step 2. So let's do step 2. order 2, order 3, order 3, order 3, order 3, order 2, and finally order 2. So actually this isn't a Eulerian graph. This is not going to be the least distance for this particular postman because we've got 1, 2, 3, 4 odd nodes. So we have 4 odds. So the odds are therefore G, B, C, and F. And we've identified them. Okay, next step. Pair up the odd nodes, making the path as small as possible. Now remember, we know that the postman's going to have to retrace his steps on some of these roads, i.e. we're going to have to create a path for him to walk down for each, connecting each odd node to each other so that he's got a path, every odd node is then even. So the options available are as follows. So let's do step 3. We could create the path, we could ask him to double back on himself so he does GB. So if he takes GB, would be 35 extra on top of the graph, he would have to take FC as well, which would be 28. If you add those two things together, you get an extra total of 63 added to the graph if he has to retrace those particular ones. What are the other options available? Well, he could go GF instead. He could go GF, which would add an extra 40, in which case he would have to retrace BC, which would be an extra 38. That would add an extra 78 to the graph. Now, which one am I going to choose? Well, I'm going to choose this one here because it's minimal distance. So I'm going to ignore this particular one here, and I'm going to ignore this one here, and I'm going to say to myself that actually he's going to have to retrace BC and retrace CB one time, so that's what to add to the extra graph. So let's look at our algorithm. We've paired up the odd nodes. I've decided in step 4 the choice I want is GB and FC doubled. Okay, so let's have a look. Duplicate the paths, we've done that, and add that onto your original amount. So that was step 4. Step 5 is then take your 440, add on the 63 extra you added, so the minimum weight is therefore 503. Step 6 says identify a path that gets us there. Okay, let's start with A. Let's go AG. There's one. So I'm going to write AG. Where do I go from here? Well, why don't we go along here? Let's go to F and then to E. So let's go to F and then to E. Let's go from here. Why don't we go to D and then to C? So I'm going to go to D and then to C. Now here I can do whatever I want really. I'm going to go up to F and then I'm going to come back to C. So I'm going to go to F and come back to C. From that point I'm going to go to B. So I'm going to write in B here. From that point, well, I'm going to go up to G and back to B. So I'm going to go up to G and back to B. And finally then, it just leaves me with the option to end up at A where I started. So here is a route and it's got distance 503, which is minimal, using the Chinese postman algorithm. Okay, let's consider one more example in a slightly more complicated case. Right, here's a network and we want to start off at A, it tells us. We want to start here, end at A, traverse every arc and come back to where we started in the least possible distance. Okay, step 1. We want to work out the total weight of this network, because if this was an Eulerian graph, that would be the minimum distance to walk every street and come back to where we started. So we're going to add up the 7, plus 2 plus 4 plus 6 plus 8 plus 3 plus 5 and plus 9. If we add those up, let's do it. 7 to 2 is 9, add 4 is 13, add 9 is 19, add 8 is 27, add 3 is 30, add 5 is 35, and add the 9 is 44. So that's step 1 done for us. Step 2 said, write down the orders of all the nodes and identify odd ones. Well, the order of each corner one is 3, because they all have 3 arcs coming out of them, and the order of the middle one is 4 because it has 4 arcs coming out. So step 2, if we identify the odd nodes, it's A, B, C and D. Step 3, we've got to try and put in arcs between A, B, C and D so that they now become even order. Okay, now let's think about it. Say if I want to pair up A and B. If I pair up A and B, the shortest way to do that is directly, and it would increase by 8. It would give me an 8 increase. If I connected these two, I would have to connect D and C. Now, how can I connect D and C? Well, either directly 6 or via E, which would give me 5. I want the minimum, so I'm going to connect via E. So I'm going to say, if I choose AB, I've got to have DEC as well, and that would have an extra weight of 5, give me a total increase of 13. Okay, well, what if I didn't go for A and B? What if I went for A and D? Say if I go for A and D. How could I connect A and D? Well, directly as 7, or via E as 6, and I want the minimum, so I'm going to go via E and give me 6 extra. So that means I would have to connect C and B, well, either directly 9 or indirectly via E as 8, so I'm going to go via E as 8. Add these two together, give me an increase of 14. I could also go from A to C. The best way to do that is directly. A to C would be an increase of 7, and D to B would be an increase of 7. 2 and 5 is 7. So that would also increase by 14. What's the best combination to double up my graph by so that every node is now even? Well, this one increases the weight by the smallest amount. So I want to have an extra arc between A and B here, and I want to have an extra arc D, E and C here. So D to E, I want an extra arc in there, and E to C, I want an extra arc in there. That will now create for me every node now will be even, and I can have a root starting in A and ending in A. What will the total distance be? So this will be step, let's just check what step we're on. This will be step 6, step 5 even. Step 5, the total distance would be the 44 plus what I've doubled up, I've added an extra 13, and give me the total minimum distance would now be equal to 57. Finally, we better draw the thing out and write it down as step 5. So, going to start at A. Why don't we go AB to just be a bit different? AB and then to C. So I'm going to say A, B and then to C. Okay, where am I going to go from there? Why don't I go down to E and back to C? So why don't I go down to E and back to C? From that point there, why don't I go to D? From that point there, why don't I go down to E and back to D? So down to E and back to D. And we're nearly home now. Why don't I go down to A and we are close now. I have to go up to E, down to B, and back to A. So that was up to E, down to B, and finished back at A. And that particular route there was a total distance of 57, and that was minimal. Okay, just a couple of things to mention. Problem with the algorithm is a problem of pairing. If we have 2 odd nodes, there's one way of pairing. That's good. 4 odd nodes, 3 ways of pairing them up. 6 odd nodes, 15 ways of pairing them. And as you increase the number of odd nodes, the ways of pairing them increases massively. Seeing as this algorithm relies on comparisons like this, it can be a very time-consuming process if there are lots of odd nodes. To finish with, I just wanted you to have a go at a couple of questions yourself, and I'll pop the answers up for you. So, pause the video when I show you this question, have a go at them, then I will show you the answer. Use the Chinese Postman algorithm to find the shortest path beginning and ending at the vertex told here. Off you go, pause the video. And now you can unpause and the answers are as follows. Just showing you what this, the way the answers work here, it's showing all the possible pairings of the odds and which one and what their total extra weight was, and therefore it chose in this case AD and CB to double up. So the final length here was 64, all of them added plus the extra 17. Again here, it paired up all the odds. The smallest way was in this example here. So therefore the total length is the total length of it all plus the extra 7 added on here. I hope you found that tutorial useful in using the Chinese Postman algorithm. Thank you for listening.